Okay, let's practice again, trying to find the greatest common factor by basically simplifying these equations by putting in some parentheses. So if I look here, I'm looking for what's common to both terms. So if I notice here 3x squared and 9x, what I can pull out of both of those is 3x. And when I see sine of 2x and sine of 2x in both of them, that's obviously common because it occurs in both terms. And 2x plus 5 to the third power, 2x plus 5 to the fourth power, I can pull out 2x plus 5 to the third power. So again, because this is a pretty complicated common factor, I tend to use brackets here to remain what's left inside the parentheses. So if I look at the first term, the only thing that's left is actually x, because I pulled everything else out when I found the common factor. So I have x minus, and it looks like the only thing I have left over here is 3 and times 2x plus 5 to the first power. So I can actually simplify what's inside the parentheses by distributing the negative 3 and combining terms. So I'm going to get 3x sine of 2x times 2x plus 5 to the third power times x minus 6x is negative 5x, and negative 3 times positive 5 is negative 15, so that would be what would be left inside. And so this is what we would consider simplifying. For the next problem here, I asked to find the derivative of this, so I got to use the product rule, and I'm going to use that skill that I had up above, namely the fact that I'm going to factor here. So let's use the product rule first. And notice that this is a u times v kind of problem. So the derivative is u prime b plus ub prime. So the derivative first is 3 times 4x plus 3 to the second power times the derivative of that inside function times 4. Then I leave the second function alone, 5x minus 7 to the fifth power, plus now I leave the first one alone, 4x plus 3 to the third power, times the derivative of the second function, which is 5 times 5x minus 7 to the fourth power, times the derivative of that inside was another 5. So now I got to look and see if I can factor this equation using the skills I was using in the previous problem. If I look here, number-wise, I have 3 times 4 is 12, and over here is 5 times 5, 25. There's nothing common to both 12 and 25. There's nothing I can divide both of those by. So now I look at 4x plus 3 squared and 4x plus 3 cubed, and I realize I can take a 4x plus 3 squared out of both terms. And then I look at 5x minus 7 to the fifth, and 5x minus 7 to the fourth, and I realize I can take 5x minus 7 to the fourth power out. And then I gotta, again, I use brackets to determine what's left inside the parentheses. So if I divide this whole first term by that common factor, I get, let's see here, 12 times 1, 5x minus 7. And when I do the same thing with the second term, I get plus 25 times 1, 4x plus 3. And so now, again, just like the previous problem, I can distribute here and combine like terms. So I'm going to end up with 4x plus 3 squared times 5x minus 7 to the fourth. And if I distribute here, I get 60x plus 100x, so that would be 160x, and minus 84 plus 75, sorry, would be minus 9, and that's what's left inside the parentheses. And this would be the simplified version of this equation. Okay, now it's time to see if we can find the derivative of some of the other trig functions. Tangent is one that you probably are very familiar with. Secant, cotangent, and cosecant you learned a little bit of last year in trig. Secant shows up a lot in calculus. Cotangent and cosecant not so much, but tangent and secant are definitely two derivatives that we do need to know. So the trick here is to realize that tangent, if you remember from trig last year, is equal to a quotient identity, which we call sine x over cosine x. These two expressions are equal. And the reason that we're going to use this is now we can use the quotient rule. And we realize here that we have a u divided by v problem. So we can use the quotient rule, which remember is u prime v minus uv prime all over v squared. So if I derive the first function, I get cosine x times, I leave the bottom function alone, minus, now I leave the first function alone, so the derivative of cosine x is actually negative sine x. I'm going to put the sine x here, and the negative makes that into a positive, okay, over the bottom one squared, so cosine x squared. Now if I look at the top there, you realize this is cosine squared x plus sine squared x, which if you remember from Pythagorean identities, again, last year in trig, this is a common one, that equals 1. So in fact, this numerator is actually equal to 1. So it's actually 1 over cosine x squared. And we like to simplify that because we remember 1 over cosine is the same as secant. So the derivative of tangent turns out to be secant squared x. And this is worth memorizing. You don't want to have to go through this all the time. So the derivative of tangent is secant squared x. And this does show up enough on the AP exam that this is worth memorizing. Okay, so let's do something similar for secant. If you remember from part of the proof of tangent, secant turns out to be 1 over cosine x. So again, I'm going to use my quotient rule because this is u divided by v. So u prime v minus uv prime over v squared. Well, the derivative of 1, remember, is 0 times, I leave the bottom one alone, minus 1 times the derivative of cosine, again, is negative sine. So I'm going to put sine there, and the negative makes that into positive, over the bottom one squared. Okay, so there's the quotient rule. So now I'm going to try to simplify this. Well, 0 times cosine x is 0. 1 times sine x is sine x over cosine x squared. Now, mathematicians look at that and say, well, that's really sine x over cosine x times 1 over cosine x. Because cosine x times cosine x gives you cosine x, squared. It's in parentheses there. And sine x over cosine x turns out to be tangent of x. And 1 over cosine x turns out to be secant x. So the derivative of secant turns out to be, actually we memorize this as secant x tangent x. And again, this is worth memorizing because this one does show up. So again, tangent's derivative is secant squared x, and secant x's derivative is secant x tangent x. Now for cotangent and cosecant, they're very similar proofs to what you saw for tangent and secant. They don't show up enough very often, so I'm going to just kind of give you these ones. The derivative of cotangent. Remember y equals tangent of x? Its derivative was secant squared x. Well, it turns out the derivative of cotangent is also something squared, but it's actually cosecant squared x. And because it's a cofunction, the derivative of every cofunction is negative. So if you notice, remember, cosine is negative sine. Well, cotangent's derivative is negative cosecant squared x. And remember, secant x's derivative was, if we memorize it in the proper order, secant x tangent x. Well, cosecant's derivative is same thing, except it's cosecant x cotangent x, and again I got to put a negative in there because of the negative cosecant, and so there's my derivative. Okay, so in reality it's not that hard to memorize because there's a definite relationship between tangent and cotangent, and that same relationship helps you memorize the difference between secant and cosecant. So study that for a few minutes and see if you can figure out how to memorize these 4 derivatives. So just a quick review of some of the rules that we've been looking at up until this point. The chain rule, remember, is a function that has an outside and an inside function. That's what we call a composite function. And the chain rule is a derivative of the outside with respect to the in times the derivative of the in. The product rule is a function where you are multiplying 2 products, sometimes known as u and v. So the product rule would be derive the first one, leave the second one alone, plus, you leave the first one alone, times the derivative of the second, otherwise known as u prime v plus uv prime. The quotient rule is for derivatives of basically fractions. We have an upper function and a lower function. So you derive the first, leave the bottom one alone, minus, then you leave the first one alone, or the top, times the derivative of the bottom, over the bottom one squared, otherwise known as u prime v minus uv prime, over v squared. So again, as you can see, it's very important that you memorize these so that you can actually find the derivatives and talk yourselves through them as you derive using each of these kind of rules. So let's practice this derivative with some equations that involve some of these other trig functions. So you notice this first one involves secant. Well, if you remember, derivative of secant is secant x tangent x. So that means the derivative of secant 7x would be the same function, secant x 7x, tangent 7x. But again, if I follow the chain rule, times the derivative of that inside function is 7. So you see how the derivative of secant involves secant of that same function, tangent of that same function. So that's why we memorize it as secant tangent, times the derivative of that inside function. We still have to follow the chain rule. Now, for y equals tangent of x squared, we have to realize that the derivative of tangent, remember, is secant squared. So the first step is to derive the outside. So tangent would be secant squared of the inside function, x squared, times the derivative of that inside function, so times 2x. Okay? Cotangent of 8x, if you remember the derivative is kind of related to tangent. Remember the derivative of tangent was secant squared of x. Well, the derivative of cotangent is negative cosecant squared of x. So the derivative of cotangent of 8x would be negative cosecant squared of, I leave the inside function alone, 8x, times the derivative of that inside function, so times 8. Next problem is, if you notice here, is a quotient rule problem. I actually have an upper function and a lower function. However, I have a square root here, and this presents a little bit of a problem here. So I want to rewrite this so that we can actually see an inside and outside function that is something that's a little bit more familiar to us. So I'm going to leave the top function alone. The bottom function I'm going to rewrite as 2x minus 3. If you remember, a square root is equal to a 1/2 power. Now, if you notice here, when I write it this way, now I can actually use the power rule on the outside function here. So again, the trick to dealing with a square root is to think of that as to the 1/2 power. So now I can go and find the derivative by doing my quotient rule. So I derive the top, so the derivative of sine 3x is cosine 3x times the derivative of the inside times 3, times I'm going to leave the bottom one alone, up to you whether you want to write it with the fraction exponent or with the square root, because we're leaving it alone, doesn't really matter. Minus, I'm running out of room here, so I'm going to leave the first function alone, sine of 3x, times the derivative of the bottom one. And this is why we took advantage of the fact that the square root is equal to the 1/2 power, because I can see now it's 1/2 times I leave the inside function alone. If I subtract 1 from that, that's negative 1/2. But remember, I got to multiply by the derivative of the inside, so times 2. All over the bottom one squared. Well, if you notice, and this is where it's helpful to go back and think, well, it's square root. Well, the square root of something squared is just that same function, so it's just over 2x minus 3. Now there's some simplifying go here, so that can go on here. For example, the 2 and the 1/2 would cancel, and wouldn't be much else. That would be the final answer here. Okay? So again, practice these rules, keep saying them over and over again as you do each one of these rules.